All right, so good evening to you all once again, and welcome to lecture 4. And lecture 4 is on matrices or matrices. Depends on how you pronounce it, but I pronounce it matrices. We've done with vectors, but we will revisit vectors again. Next week, we'll talk about transformation. All right, Daniel, go on.
Yeah, hello. Please, I have a question with regard to the previous slides.
Okay.
Sorry to interrupt you, but
Oh, don't worry,
um,
Daniel.
please, with the Gram-Smith process of orthogonal
Yes,
basis,
yes,
is always that the E1, the orthogonal basis E1 is equal to the V1. Is it
yes.
always like that? Okay.
Yeah. Yeah, go on. Are you done? You finish your question before
Yes,
I come
please.
in.
That was the question. That is always E1 is equal to the V1, or there is
Yes,
some
we
case where it will change.
no, we need that to be able to help us to find the other basis. So that one is always be set it to that. Hello, Daniel.
Yes, please. Yes, please. Thank you.
Yeah, we set it to that to help us. Okay. And when we do that and we get zero, it means they are all dependent, right? And we stop.
Yes, yes,
But we
yes.
set it to that so that we'll be able to get the rest. Okay, thank you.
Okay. Thank you, sir.
Okay, so today I want to talk about matrices. And what do you know about matrices? Just uh, let me create a poll right now. Tell me something, just one line. I know the poll is limited. I think you can't type a lot of things. So just be concise, just go straight to the point. Tell me what you know about matrices. Okay, so what do you know about Matrix? Oh, yeah. It's not the movie. Oh. It's not the movie Matrix. All right. So, 3 minutes. Tell me what you know about matrices or matrices. Okay. Albert said rectangular arrangements of numbers. Okay. Richard said numbers arranged in rows and columns. All right. Daniel said set of vectors arranged in columns and rows. All right. Who else? Charlotte said rectangular arrays of numbers or symbols arranged in rows. All right. Manal, an element position is described by its row and column. Okay. Yes. Who else? Joshua, arrays of vectors or a linear transformation. Wow. That is good. A set of real numbers that are arranged in rows and columns. All right. Who else? Albert said, okay, rectangular numbers. All right. Okay. All right. Charlotte. Okay. Esther, Precious, a rectangular array of numbers arranged in rows and columns. Okay. Emmanuel. Okay. Steven just joined. Thomas, Marcia, what about you? All right. So, I mean, all the things that you've provided, all the answers you've given, I mean, they are all correct. All right. They are all correct. And let's proceed. Okay. So, this is what we are going to talk about. Now, we are going to use 3 weeks. We are going to use 3 weeks. We are going to use 3 weeks, which will talk about matrices and also the effect matrices have on vectors. And we'll also learn about transformation as well. Then the last one is going to be the single value decomposition, where we'll talk about eigenvalues and eigenvectors, right? And by the time we finish, you guys will be machine learning engineers. or data scientist. We saw that vectors, they are the fundamental building blocks that represent a single point of data, right? So if you want to describe a sample which is single data, for example, I called precious, that is a single sample or a single observation. I can use vector to represent her features. Now, if I want the whole class or the participants, all of you over here, using a single vector will be a problem. And I need to use a different method. And that is where matrices or matrices comes in here. So machine learning involves working with a collection of data points, not just one. Those of you who have used or you have been doing the coding where you have your data sets, you realize that when you use pandas and use the NumPy, it is just a collection of data points. These data points, that is not a single data point, it's just numerous of them. Using vectors to represent it will be a problem for us. So what we have to have a better way to organize our data, to manipulate these data efficiently so that we can write better algorithms for our computer to be able to compute. When we talk about matrix, from the definition you guys give, we said it's a rectangular grid of numbers arranged in what? Rows and columns. A rectangular grid. All the definition you guys gave was fantastic. If a matrix have m rows and n rows, we say what? The dimension is what? Mn. Okay, so I have a matrix, and sorry guys, my writing part there, the guy is delaying me. He promised me this, but still he has not gotten back to me. So I'm just praying next week I'll be able to get it so that I can teach. Okay, so we have this. Now, if I have A here, then B here, then my C here, then my D here, right? Now, you will tell me I'm having two columns at the top here, then two rows here, right? So the dimension is the row by the column, which is 2 by what? By 2. That is the dimension. Okay. Now in machine learning, they can also ask you to find the size of your data set. So the size of your data set is when you multiply the row number by the column number, and you get 4. Yes, Marcia, go on, ask your question. Hello, Marcia, go on, ask your question.
A mistake, please.
Okay, all right, that's fine. Okay, so that is your size, which is 4. So the size tells you the number of entries or the number of elements you have in your matrix. So when you are dealing with images, so one of the things that we do is we want to find the total number of pixels. And how do you get that? So to get a total number of pixels, you just multiply your resolution, which is the width, by the height, and that'll give you the total resolution. Okay. All right, so let's take this data. So let's assume one of you, maybe Albert, is working on a project, and this is the data Albert collected. Now with this data, we have some features over here. And the first feature we have is the size. The second one we have is the bedroom. And we also have the price. Now what we do, so the size, we have some data that we've collected, and this, so the size, we have the size, and we have the bedroom, the bedroom, we also have the price. So we said we can use a vector to represent this. So if I have a vector called A, which I can use to represent the first observation, which I have 1,500, then the bedroom is 3, then maybe the price is all 300, right? All right, which is my first observation. My second observation, which let's make it A1, so A2 can also be represented, okay, by 1,200. Then I have 2 over here, then also I want 250, right? All right. Okay. Then we also have A3, which is the third one. So we're done with this, we're done with this. Okay. Then I can also put that one in the vector form, which is 1,800 by 4 by 380, right? Then I can also do it for the A4, right? So now, why am I doing this? I'm just showing you something that when it comes to vectors, you realize that vectors are just when it comes to matrices, not vectors. When it comes to matrices, you see that just a collection of what vectors that we put inside. Okay, so I can represent each observation as a vector. But if I want to organize it, the best way to do is using it in the form of what? A matrix. So here, if you look at it, you will tell me what is the dimension of the matrix. If I ask, what is the dimension? You can go on and type it in the chat. What is the dimension? What is the dimension? So A, all right, so I have, okay, all right, so someone is saying 4 by 3, 3 by 3, 4 by 4, 4 by 3. All right, so let's count the number of rows. So we have, this is row 1, row 2, row 3, row 4. So here is 4, right? Times. Then let's count the number of columns. 1, 2, 3, which is 3. So this is a matrix of dimension 4 by 3. So there, we want to find the size, we multiply this, you get what? 12. So we have so we are having 12 entries. We are having 12 entries. Okay. We are having 12 entries here. All right. So you see that we can pick each observation and get it out of the matrix, and we can also put them back, right? So if you look at it, this is feature 1, this is also feature 2, this is also what? Feature 3, right? And we can pick each feature and as a matrix as well. All right. So why use matrices? Because we said it's compact and they offer a concise way to store and refer to large amount of structure data. So that one is concise. You can put your data, arrange it in a way that you can do computation with it. Then also it's also the standardized format. That means it is what is used in many algorithms and software libraries. Many algorithms and software libraries relies on what? Matrix for their computation. Then the last one, foundation for operation. Now, matrix operation allow complex data transformation and calculation to be done across what? An entire data set. Now, machine learning and deep learning, they all rely on this transformation. And that is what we'll talk about next week. When a vector is being transformed from one space to another, it can be the same space, but this is done by a matrix. It's done by a matrix. And this deep neural network or this deep learning, they are neural networks, they are just transforming the data from one space to another, and they use matrices. So this is, the mathematical definition where I give example, just a rectangular array. I'm using here array. I want someone to tell me why I use array over here. You can type in the chat or mute yourself and tell me why I use array over here. Why did I use array over here? You can type in the chat or mute yourself and tell me something. Why I use array over here? A matrix is a rectangular array of real numbers, all right? Okay. Columns and rows? No, I won't give you that. You already saw the definition earlier on that a matrix is having a grid, right? So the column and rows will still apply over here. But there's the main reason why we use arrays. Okay. Mariama said the index of input are fixed. Mariama, no. I will not give you. Uniformity of the data type. Yes, that is what I want. Uniformity of the data type. Now, one thing about arrays is if you are dealing with, whatever specific number, that is what you're supposed to deal with. So we normally say in programming that it has to be of the same type. It has to be of the same type. If this integer you are dealing with, make sure they are all integers. If they are real numbers, make sure they are all real numbers. They are complex numbers, but don't mix them. So arrays, they must be of the same type. You can't mix them. You can't mix integer with floating point. That is going to be a problem when you are doing the computation. So the uniformity of the data type is very important. So when you talk about it, we are dealing with the uniformity. So here, if you look at it, you will tell me that they are all real numbers, but this one, it will be definitely integers. Then this one will be real numbers, right? This one to another real numbers. Here, zeros, then here to the integers. So they are all rectangular or a grid of a rectangular array. And here you will tell me that we have 2 rows and 3 columns. So to make it 2 by 3. Okay. And here too is going to tell me 4 rows by 2 columns. So you get 4 by 2, right? All right. So let me proceed. Okay. So this is the notation where Mariama said the indexing. So the indexing, irrespective, Mariama, irrespective, if you are doing a collection of items, you can do that, okay? But because we said an array, that's why I said it must be of the same type, right? So here, your indexing comes in over here. Their positioning is crucial. Their positioning is crucial. So here, you need to specify. So here, we move from the first row to the nth row. Then here, move from the first column to the nth column. Okay, so this vector is of the size. When you multiply the number of rows by the number of columns, you get the size. So the dimension is m by n, where the m denotes the number of rows and n denotes the number of columns. Now we saw that you can also have equal vectors. We can also have the same thing in matrices. But before we come to that, when a matrix is square, we say that the number of rows equal to the number of columns. The number of rows equal to the number of columns. So a practical example is I have 1 here, then 2 here, then 3 here, then 4 here. So this is a square matrix. Why? The number of rows equal to the number of columns, right? Now, we also have column vector and also row vector. This is very, very important when we get to when we are multiplying a matrix by a vector. Now, a column vector can also be a matrix. A column vector can also be a matrix. Then a row vector can also be a matrix. But we have to look at the dimension. That is what is important. That is what is important. What is important is the dimension. If you can look at the dimension properly, you can do matrix multiplication very fast. So we have a column vector. Let's assume we have a column vector 1, then 2, then 3 over here, right? We are saying that this vector can also be expressed as a matrix, but it's going to be of 3:1. 3:1. Now it's 3:1. If you look at it, it's trying to tell you how 3 rows and 1 column, and that is what is being expressed over here. So the M there we say stands for the number of rows, right? So when you see a matrix of a dimension M is by 1, let me use the word by, not is 2. M by 1, that means that is a column vector. Okay. Then we can also have a row vector. If you look at a row vector, I can also write this, can transpose this. We learned that 1, then 2, then what, 3. If I transpose this, you see that I have only one row, then what, 3 columns. And that is what we have, which is 1 by what, n. This is a matrix, but it's a what? It's a row vector. It's a row vector. All right. So M by N matrix contains M columns. M columns. So when you look at this, which we said the dimension is 2 by 2. If you are looking for this, or we are using this definition, then we are going to say that we have what? 2 columns, which is this column, 1, 3, then this column, 2, 4, right? Then also have what? 2 rows, which is 1, 2, then what? 3, 4. So I want you to see matrices as just column of vectors and also rows of vectors that has been arranged. A 1 by 1 matrix is just a scalar. So when you have a scalar, that is a 1 by 1 matrix. You have a matrix of size 1 that can also be expressed as what? 1 by 1. Why do we need it? We need this purposely for computation. So a matrix can also be, a scalar, not a matrix. A scalar is also a 1 by 1 matrix. Now the number that you have, which is the indexing, like what Mariama said, we can use these positions, the I and the J, to denote it. So if I use A, which is the I and the J, okay, the I there can be any number, the J also there can be any number, depending on what indexing you want. So this is referred to as the row indexing, the J is referred to as the column indexing. So if I say A, which is 1, 2, I mean go to row 1, column 2. If I say A 4, 1, it means go to row 4, column 1. That is the meaning. Let's talk about equality matrices. So two matrices are equal, A and B, if and only if they have the same size and all their entries are the same. This is obvious. So if I have a matrix 1, 2, and 3, 4 over here, that is the entries, or these are the entries. All right. Now I can have another one, which is 1, 2, and 3, 4. Then I can have another one, which is also 10, 11, 12, and what, 13. Okay. You tell me that, say, this is equal to that, but this is different. Why? They have the same entry. The entries are equal. They also have the same dimension. They also have the same size. We'll find out when you have a matrix like this, how do you call it? We'll get to that. Let's talk about basic matrix operations. As I said, next week, our main focus will be on transformation. But let's understand these basic operations so that when you're doing the transformation, things will be clear enough. When you have a matrix, we can add it, we can multiply using scalar multiplication, and also you can also have what? Matrix multiplication. In vectors, we saw that if you take the vector spaces, the addition hold, scalar multiplication hold. These were the two things that we built on it. Whereas we can have the additive, which is the inverse of it. Then we also have the distributive and also the associative. All these things, we got it, or we're able to obtain it from the two operations, which is the addition and the scalar multiplication of vectors. Now, in matrices, the one has been added, which is what? Matrix multiplication. And this is what machine learning and deep learning, they all rely on. We transforming from one, or taking one vector space, or taking one vector from one space to another. And that is matrix multiplication. All right. So when you are adding matrices, like the way what we did in vectors, we saw that in vectors, you do what? element-wise addition. So if I have a vector A here and I have a vector B here, and you ask me to add this, I have B, another vector B and C over here, I can only add the A to the B and the B to the C. The same thing also holds in matrix, entry by entry addition. So if I'm adding two matrices, the one will be added to the three, then this also will be added to this, then this will also be added to that, and this will be added to this. This is something simple and easy. So it's the same thing like what we did in vectors, just entry elements wise addition. So this entry and this position, they will add, this and this will add, and this will add. All right. So that is the mathematical formulation that the sum of two matrices A and B is just the addition of their element-wise position, right? So A is here, A, which is I, then J, then B, I, J. So here they must be the same, right? So if here is 1, here also must be 1. If here is 2, here must also be 2 for you to add it. Add them. Then the next one is scalar multiplication. We saw this when we were dealing with vectors, that if you have a vector and I have a vector again, which is 1, then 2, and 3, right? So if I have a scalar, which I have a scalar minus 2, we saw that the scalar is going to multiply all the elements. So I'll have minus 2 here, I'll have minus 4 here, and I have what, minus 6 here, right? The same thing also applies in matrices, which you have a scalar, and the scalar is going to multiply each element, each entry. So the 3 will multiply the 1, you get 3, 3 will multiply the 2, you get 6, then 3 will multiply negative 1, you get minus, then minus 3, then you get 0. So these are things that, I mean, is similar to what we did in vectors. So I shouldn't waste time here. All right. Now, what is needed is the matrix multiplication or the matrix product. So let's look at something here. I have two vectors, and we said the vectors can also be written in the form of what, a matrix. So whether it is what, m by 1 or what, 1 by n, we saw that. Okay, so let's have this vector, which v, that has been transposed, and w, which is a column vector. So I have my v over here. Okay, so this has been transposed, is now what, a row vector, and a row vector we said can be written as what, 1 by what, your n, right? Then I also have the w, which also have been it's also in the column vector. So my w, please, Joseph, can you mute yourself? Okay, so my w, or this w, can also be written as m, right, by what, 1. We saw that. Okay, so we want to multiply this. We want to multiply this. Now you've seen this thing already. Okay, you will tell me that, say, you are doing what known as what, dot product, right? We did this one in vectors, where this multiply this, this multiply this, this multiply that. But in vectors, mostly, or not mostly, in vectors, we have two ways that you do the multiplication. The first way is when we use the row to multiply the column, then we can also use the column to multiply the row. But when we are doing that, there's a theory known as the compactability. You have to be careful about that so that you don't mess up. So here you see that the row, which is this row, is being used to multiply the column with this column, right? So this goes here, then this goes here, then this goes here, then this, all the way that. So when you do that, you end up getting, which is a scalar, and that is the dot product. That is a dot product, right? We can also do the reverse, where we try to turn it. But when we turn, will it work? That is something that we have to always ask ourselves. So when we are multiplying vectors, we have to be very, very careful with the dimension. So this is what I showed. Now, if you look at it here, we have the vector over here. Now I want to multiply two vectors, which you can also make it matrices, right? So I want to multiply this and that, find the dot product. Now we transpose one so that the dimensions or the compatibility will be obeyed. Then we can do that. So I transpose one, then I can multiply. I can do the reverse, which I can swap it. But if you look at it, you see that the W has also been transposed. Okay, then I'll multiply with my V. Then at the end, I'll get what? My dot product answer. Now, this is very, very important because if the dimension doesn't agree, you won't be or you can't be able to do that. Okay, you can't be able to do your matrix multiplication. We'll find out. All right. So it should be emphasized that the matrix product between two columns is not defined. That means if you want to multiply two matrices, which a column one, so which is I have which is 1, 2, 3 here, and you want me to multiply this by 4, 5, and 6. It's not defined. Why? There's a rule, and that rule we talk about it. This is not defined. This is not defined. For us to be able to multiply this, we need to transpose one. We need to transpose one. All right. So how do you do that? We can keep the column, the first one, okay, and transpose the second one, which we have 5. 5. This is my writing pattern. That guy is just wasting my time. Okay, so we transpose this, or we can also, as you saw, we can transpose this, which is the second one. So if you transpose, let me look at it properly. All right, so you transpose the first one, multiply with the second one, or you transpose the second one, multiply by the first one. Here, what do? We kept this. Then we transpose the second one. So what I'm going to do is I'll keep the second one and I'll transpose the first one. And it should still work, which 4, 5, 6. Then I'll transpose the first one. 1, 2, 3. It should work. Right. It should work. So if you should do this, all right, if you should do this will multiply by this, you get 4. This, so we get 4 here, right? Then plus this. No, we are going to get two different vectors. I don't have space, so let's get to the next one so that I'll talk about that one instead. All right. Now, if you have a matrix of dimension or of size m by n, okay, then you have another one also of dimension or size m by p, and it asks us to multiply. So I have my A over here, which is m by n. Then I want to multiply by another matrix of dimension n by p. All right. So we say that the inner dimensions has to be the same. The inner dimensions are not the same. You can multiply. So let's go back. Let's find out. Okay. Let's find out. So here, we wanted to multiply this. Here, what is the dimension? I want someone to tell me the dimension for this. What's the dimension for this? You can type it in the chat. What's the dimension for this? All right. So 3 by 1. That is correct. What about this? What's the dimension for this? All right. So 1 by 3. That is correct. All right. So you see, this is 3 by 1, 1 by 3. The inner dimension must be the same. So 1 and 1. Okay. So that when you multiply, we end up getting what? 3 by 3 matrix. That is quite a lot. I didn't want to do that. All right. Now let's look at this. Here, I think the same thing. Yes, the same thing. If you multiply, we end up getting that. So the inner dimension, they have to agree for you to be able to or they have to be the same for you to be able to multiply two vectors. If not, and your result or your resultant, the vector that you will get is going to be the row by the column. So here C is going to be M by P. Okay, M by P, right? M by P. So this is what you're supposed to get. All right, so this is in the generalization that we have a vector, sorry, we have a matrix of this, and we have another one of that. You see the inner dimensions KK, and the result or the resultant matrix is what? IJ, obviously it. So that is that. The bad news is that matrix multiplication is not commutative. That means BA is not equal to what? AB. If you multiply two matrices, if you reverse it, doesn't mean that you are going to get it. No, it's not necessarily. Okay, that means we might have scenario where it might work, but in a general sense, it is not commutative. All right. So let's look at this. Now here we are doing some multiplication where the row, so this multiply this and this multiply this. So if you do that, okay, you get this times this, which is what? 3, right? Then plus what? 0. So your answer is equal to 3. Now if you look at the dimension, what's the dimension here? What's the dimension here? 1 by what? 2, right? And what's the dimension here? What's the dimension here? 2 by what? 1, right? So if you look at it, you see that your inner is, they are the same, right? So that is why we had what? A scalar, which is 3. Now let's come here. Here, what is the dimension? The dimension is what? 2 by what? 1. What's the dimension here? 1 by what? 2. So the inner, the same. So you get what? 2 by 2 what? Matrix, as you can see. Now I want you to be very fast when it comes to that, so that you can do the calculation fast and quickly. Okay, yeah. A minute. Someone is saying he's having issue with logging in, and I don't know. Charlotte, if you can assist the person on the platform, right? Maybe tell him or her to log in and log out again. Right. So let's continue. So let's look at this. Here we want to multiply. Now we say we use the rows. We multiply what? Our column, right? So if I open this big one, will multiply this, and I'll get what? 0, right? Then this will multiply this to get what? -2. That is the first. Then this I get 1. This will multiply this, which is 1. Then this plus what? 4, right? Then we come here. We come to the second row. This will multiply this, which is also 0. Then this will also multiply this. Sorry, again -4. So -4, right? Then this will multiply this. You get 3. And this will multiply this. You get what? 8, right? Now, if you put everything together, you get what? -2, you get what? 5 here, then you get what? -4, and you get what? 11. Now, in machine learning, you are going to have a lot of them, and if you want to do it manually, it will take you forever. So in Python, we have libraries. NumPy can help you work this thing quickly, and the thing is, they will show you guys this week. Now, when we also change it and we try to multiply, let's see the proof. So it has been swapped. Let's see the multiplication whether it will work. This also will give you. So we said the row will deal with the columns. Okay. So this will multiply this. You get 0. This will multiply this. You get +3. And this will multiply this. You get 0. This will multiply this. You get what? 4. So this will multiply this, which is 0. This will multiply this, you get 4. And this will multiply this, you get -1. Then this will multiply this, you get plus, you get 6, right? Yes. Now this will multiply this, you get -2. Then this will multiply this, you get what? 8, right? All right, so if you put things together, we get what? 3 here, you get what? 4 here, you get what? 5 here, then you get what? 6 here. If you look at it, there are two different matrices. They are not the same, right? So he said matrix is not necessarily or commutative if you want to multiply it. All right. But the beautiful thing is they are associative, and this, those of you who go and do computer, or if you're a computer science student here, or if you are not even a computer science, and you happen to go and do anything related to advanced data structures, this is something that they ask us to prove when you have this, and we were supposed to write an algorithm to implement this. And it's so beautiful that although matrix is not commutative, but they are associative. That's the beautiful thing about it. You can prove it yourself. You can have matrices and prove it. And they use it in dynamic programming. I don't know whether I'm correct, but they use it in dynamic programming. All right, they use it in dynamic programming. All right. And it's also distributive. It's also distributive as we saw in vectors. So it's like we expanding. So we can add a two matrix and multiply, or we can expand it, and whatever way it will store to work. Right. Now, the difference between matrix algebra and ordinary algebra is that you need to be careful not to change the order of the multiplicative factor without proper justification, as I said. All right. The dimension is very, very crucial. So we realize that if I have a matrix of dimension 2:1, I can only multiply this by what? Another matrix of dimension 1:what? So 1/2. Why am I using is to? 1/2 to make sure that the dimension agrees, or else it will not. It will not. Okay, it will not be possible. So you have a matrix of dimension 2/2, and you want to multiply it by a matrix of dimension 3/2. That will not be possible because the inner dimension doesn't agree, so it will not. So that is why here it is saying that you make sure that what you check your multiplicative factor. Very, very important you check that. But we saw that we can have a matrix, or we have a matrix A, B, C, D, and I show you the demo where we are multiplying the row by the column, right? The row by the column. So if here is E and F, we can also turn it and make sure that we also multiply the column by the row. So matrix multiplication acts by multiplying row by column. That is what we've been doing so far. Okay, so all the multiplication I've been doing, it is the row multiplying the column. So where I pick my rows, then they execute on the columns. So this will multiply this. I have what? A, E. Okay, and this will multiply this, then I'll add it, which is what? B, F, right? Then I'll count for this row. This will multiply this, which is what? C, E, then plus this will multiply this what? D, F. So this is what we've been doing so far, where the rows act on the columns. Now we can also have another way out. So this is the demonstration or the example where we have the rows acting on the column. All right, so here, if you look at it, you can tell me clearly that it is what? 3 by what? 2, right? And this is what? 3 by what? 2, right? So, no. So I made a mistake. It's supposed to be 2 by 3. Let me clean it. Okay. Forgive me. It is 3. I say it like that. Let me raise it right now. All right, so it is 2 by 3. All right. Sorry, guys. All right. So it is 2 by 3, then here is 3 by 2, right? So here I have the inner dimension agreeing. So at the end, we get what? 2 by 2 matrix, right? Now, if you look at this, I have 2 again by 3. Then here, it is 3 by 1. So the inner one agrees, so I'll get 2 by 1, and that is what we are doing over here. Then DS2, if you look at it, also what? 2 again by 3, and here to the same thing, which is what? 3 by what? 1. So the new one agrees, so we have what? 2 by 1. So here the rows act on the column. So let's pick this one. Maybe this is simple. So we can do this. So this comes here. So let me pick my big bracket here. So this will multiply this, I'll get my 3 here. Then this will multiply this, I'll get plus 0. right? And this will multiply this, I get what? Minus what? 2. So that is that. Then I come to the second row, this will multiply this, which I get my 6. And this will multiply this, I get my 0. And this will multiply this, I get plus what? 2, right? Okay. So here is 2. Let me write it well. So if you sum everything, you end up getting 1 rather, then what? 8. All right. So this is where we are acting the role on the column. You will do the reverse. So take note. All right. Now, when you take the matrix, as I said, there are vectors that we have in the matrix, right? So we can also say that, okay, so I have a matrix A and B. Now, let's assume I have 1 here, then I also have 2 here, then I have 3 here, then I have 4 here, right? Then I have another matrix which is also 10, then 11, then 12, then here is 13, 14, then what? 15, right? I have this. Now, what you're saying is you can have your matrix all right. I have, which is the first matrix, as you can see, right? Then I will pick each column, which here there are 3 columns here. I'll pick each column, which I'll have the first column. So let me use square bracket. I have 10, 13, right? Then I can use another comma. Then another column here, which is 11, 14. Then another one, which is 12, 15, right? Or 15. All right. So this can come in and come and multiply and say it's possible. Let's find out whether it's possible. So let's pick the first one. Then if it is possible, we stop. So 1, 2 here. Then I have 3, 4 here. Then here I have 10, 13. How will you know this is possible? Let's find a dimension here. This is what? 2 by 2, right? This is what? 2 by 1. Wow, this is possible. So the inner ones being the same, that means I can multiply this. So you see how vectors and matrices, they play a role in computation. For us to be able to multiply solve complex equations, you see how these things, are being used. So if you want to multiply 2, you just take the second matrix, pick the column vectors out, and use it to multiply the first matrix. And it is possible. So if you can write an algorithm to implement this, I can do computation very, very fast. And that is what are being done in machine learning and deep learning. So the rest, when you take or have the slides, you can do it yourself. Right. So multiplying a matrix of dimension n by n by the standard basis. You know the standard basis? That is something. Do I have any space over here to prove? Okay, so let me get a space for us to prove this. So, but let me explain this. When we have the standard basis, what are some of the standard bases? Give me an example of any standard base that you know of a vector. Standard base. Be quick. Any standard base? Any standard base? Okay, so 1, 0, and its counterpart is what? So 0, 1. Yes. Now, yes, thank you. Yes. So when you have a matrix and you multiply a matrix by a standard base, we are able to get the position or the index of a specific entry of the matrix. So I have a matrix over here, 1, 2, 3, 4, right? 4. Now, when you look at this, if I want to get the first column, all I have to do is to multiply by this. If I want to get a second column, all I have to do is to multiply by that. Now, let's find out whether that is true. All right, so I have this. Now, let's pick the standard base. Now, if you look at the dimension, here is 2 by 2, here is what 2 by 1, so we can multiply. Okay, so the rows will act, so this will multiply this, I get 1. This will multiply this, so plus 0. This will multiply this, I get 3. This multiplies all 0. So what did I get? Which is 1, 3. So you see here, when you have your standard base, okay, you can be able to you have a matrix and you multiply a matrix by a standard base. You can get the independent or the individual columns that you are looking for. So here, if I want the first column, I just have to multiply and see it has come out. If I want to get a second column, you just have to multiply by this and also come out. Right. Now, what about if you're looking for the entry? If you're looking for a specific entry, for example, if I'm looking for 1, what can I do? Because here, when we multiply this by the matrix, we're able to get the first column. If we multiply this by, we're able to get a second column. But what about if I need an entry, which is the first entry or the second entry or the third entry? And this is where this formula comes in, where we multiply. So if you look at it, here is supposed to be transpose. Sorry, let me put it over here. I need to correct that. Okay. So here, what we'll do is we multiply the vector, which is the base by the matrix. We do that. Then after that, we transpose and we can do that. So let's assume I want to get this, the 1. So what I'm supposed to do is I'll multiply my matrix, which is 1, 2, 3, 4 here, by the j. The j is the second one, which is 0, 1, right? Will you even give me the first? Well, I'm not sure, but let's find out. Okay, so here we multiply, so we get 0, 0 plus 2. Then I think you are going to get 4. What am I doing? 4 here. All right, sorry guys. So which is 2, 4, right? Then what do? We transpose the first one. So if you transpose the first one, we end up getting 1, 0 rather. Then we multiply it. We need to transpose it so that, the dimensions work. All right, so this will multiply this, which is what? 2. The other one will become 0, so 2. So here, I think I was picking the 2 out. Right? So you can get your individual entries by using this. You can get your individual entries by using this. So here, it was the 2 that I was picking out. So you see how we manipulate vectors and matrices and able to use it to do what? Computation. All right, let's proceed. Now, matrix multiplication is defined by multiplying row by column. Okay, Mariama, go on. Mariama, ask your question.
I have a question with the you just did.
Okay.
Yes, with the transpose, why is it that you use the other base, not the one that you use to multiply it? I don't know if you get me.
Yeah, I understand. Now look at your indexing. This is I, this is J, right? Now the I, we learned it in vectors. This is the I, the base, the standard base is what? Is this, right? And this is the J. Sorry. The J is the 0, 1, right? So if I'm doing the transposing, I need to do the transposing on the I, not the J. That is why I did that. Have you seen it? You pay attention to the values.
Yeah, I've seen it.
The index. Okay, so let's proceed. So all this while we'll be multiplying the rows by the column. That means the rows act on the column. We can also do the reverse, where the columns now is going to act on the rows. The columns will act on the rows. How do you do that? So let's have a matrix which of this. So when you have this matrix m by n, you are going to tell me it's going to have what? How many columns? N columns, right? So I have N columns. So M by N. So I have what? N columns. Then I have another matrix, which is this. Now here, you are going to tell me it's having how many rows? N rows, right? Now you remember I said at first that you can multiply two column vectors. Sorry, two column matrices. Sorry, you can multiply two column matrices. It's not possible. So what we do, we need to transpose one, right? Transpose one. So if I pick the column, it means I need to pick what? My row. You get it? So if I pick row, it means I need to pick what? Column. That is the whole thing here. If you pick row, the second one must be what? A column. So if the first one is a row, remember the second one should be a column. Okay, if the first one is a column, don't forget the second one should be what? A row, because the transposition is very, very crucial for the multiplication to happen. All right. So all right. So if you look at it over here, we are multiplying, which so these are the columns, and we are transposing the second ones for the multiplication to happen. So let's look at this. Look at this example, then we'll be able to understand what is happening here. So let's assume this is my A and this is my B, right? So if this is my A, this is my B, we can pick the column of the A, then we pick the row of the B. That is what. So we should transpose that. That means we are not going to use the same column. We said we can multiply two matrices that are in column wise. So if you look at the 1, 3 over here, 1, 3, then we have 0, -1. All right. Then we can pick the second one. Sorry, what am I even doing? There's no plus here. Let me hit it. All right. So we pick the second one, which is the column 2, 3. Then we pick the row 2, 3 again. Sorry, what am I even doing? It's 4, not 3. Sorry, guys. Then we pick 2, 3. All right. Now, how do you multiply this? Let's find out how this is done. All right. So we multiply this by this, and we multiply this also by that. But we are going to have two different matrices, and you need to add it. So this will give you the first matrix. Then this one also will give you the second matrix, then we can add it. So this will multiply this, you get 0. And this will multiply, get -3. Think, sorry, this will multiply this, sorry. So it's supposed to be 1 rather. And this will multiply this, you get 0. And this will multiply this, you get -3. Let me take it again. So this will multiply this, you get 0. This will multiply this, -1. This will multiply this, 0. This one, -3. Then here you come here. What did I even write? Wow, you guys did not correct me. So here must be, okay. So it must be a row rather, which is 2, 3. Okay. So this will multiply this, which is 4. And this will multiply this, which is 6. This will multiply this, which is 8. This will multiply this, which is 12, right? So if you put it together, let me write it well. We can add it. This will give you 4, right? This is 5. This will also give you 8. Then this will give you 9. And that is what we have over here. Now, this is very, very crucial in neural network, deep learning. This, what I've done over here, is very, very crucial. So, there are two important, special matrices. We'll come back to this. We'll come back to this one. Okay, but let's proceed. There are two important special matrices. The first one is a 0 matrix. This one is obvious, right? All the entries will be 0, right? So all the entries will be 0 irrespective of the dimension. Okay, so we can have this is 3 by 2. So all the entries being 0. Right. Now, when you have a 0 matrix and you add it to any matrix, it will still give you the same matrix. So that is where the additive unit comes from. So which is like a 0 plus 10 is the same thing like 10. So we saw this in vectors. Then we also have the identity matrix. The identity matrix along the diagonal, they are values, which is 1. Apart from that, any other place it is 0. So this is the diagonal here. You are going to see 1, 1, 1, 1, 1, 1. Now, if you look at it carefully, you will see that each column is just a base. So if a standard base, so if I have, let me use this, maybe 3 will be fine, or I can even use 2, which is 1, 0, 0, 1. This is an identity matrix. If I take the first column, this is a base, which is the I, right? Which is equal to 1, 0. Then I also have the J, which is equal to 0, 1. Okay. Yeah. So each column can also be seen as what? As a standard. So if you want me to express this, then I can also go ahead and write it that this one is just I. All right. Then sorry, I'm writing the I. Then what? J. Right. That is that column wise. Now the columns are the standard basis I've already explained. All right. And the beautiful thing is that we can see the identity matrix as like a 1, like normal algebra 1, because irrespective, if you multiply by a matrix, you still get a matrix back. We'll use this one in inverse when I'm talking about matrix inverse. All right. We'll do it next week, but today we'll be introduced to it. So the generalized form is this, that if the identity matrix multiplies the A or the A multiplies the identity matrix, okay, you still get what? The matrix back. All right. Now the identity matrix is a particular example of what? Diagonal matrix. So diagonal matrix, you understand the name. That means the matrix is having a diagonal values. Apart from that, any other place is what? Is 0. So if I have a matrix over here, 1, then 0, then 0, and 2, this is what? A diagonal matrix. That means on a diagonal, the values you have, the values. Apart from that, any other place or any other index or entry is 0. Any other entry is 0. And this is how it is expressed. And if you have a diag like this, it can also be expressed this way. That shows you that only the diagonal values, only the diagonal will have values. Apart from that, any other place is 0. So when you have a square matrix, which you have this square matrix, and it's also an identity matrix, right? Sorry, not identify, identity matrix. Okay. The diagonal will be 1. So what he's saying is that when you have an identity matrix, which is supposed to be a square matrix, which we saw here to be 0, 1, 0, then 0, then 0, then 1, then 0, then we also have 0, then 0, then 1, right? All right. Now it's a diagonal matrix, so we are saying that this place must be 1. That means I is equal to the diag. Okay, 1. That means is 1. All right. Then we also have what is known as upper triangular and lower triangular matrices. So this I'm not going to waste time on it. But if you look at it, you will see that this is the upper triangular. This is the diagonal. Okay, so the diagonal and above the diagonal, all these things are all the entries are non-zero. Okay, below the diagonal, all the entries are 0. So below the diagonal, all the entries are 0. So this one's upper triangular. Then the lower triangular will also be above the diagonal, all the entries are 0. So this is a diagonal. So above that, any entry you see over there is what? Is 0. Okay. Now, what we want to talk about is transposes and symmetric matrices. We saw the transpose earlier on, where you change the columns, becomes what? Rows. So if I have a vector, we did it in vectors. I have A, then B, then C. All right. If you transpose this, we are supposed to get what? A, then what? B, then what? C. Sorry, which is this. That's what we done. Okay. In matrices also, we can also do the same thing. But when you say something is symmetric, that means when you transpose it, it ends up being the same thing, right? That means it will not change it. But one thing about transposing a matrix is that the diagonal doesn't change, it stays the same. Who can give me an application where this thing is applicable? Because we want to transpose a matrix, but the diagonal is not changing, it's staying the same. So we have a matrix here, 2, 3, 4. Now let me transpose it. If I transpose this, I expect the columns will become rows. Okay, so this is my column, becomes 1, 3 here. Then this one 2 becomes 2, 4 here, right? That's the transpose here. Look at the diagonal, it's still the same. What do you think is happening here? An application in machine learning where you all right, you will find out later. All right, so the transposition is crucial. An example is what I've given over here. Okay, so if it's a square matrix, let me use that. If it's a square matrix, that's why the diagonal doesn't change. But if not, so this is not a square matrix. If you look at it, the dimension is 2 by 3. But if you look at it here, we are saying that if you pick a column, it becomes a row. If you pick a column, it becomes a row. If you pick a column, it becomes, that's what matrix transposition. But the beautiful thing is a scalar. We said a scalar is of dimension 1 by 1, right? So whether you transpose it or you don't transpose it, it still ends up being the same, right? So the transposition of a scalar is still the same scalar. And when you transpose twice, this we saw it in vectors. When you transpose twice, you end up with the same thing. So if you have a matrix and you transpose it and you transpose again, you end up with the matrix. We saw this in vectors, that when you have a vector and you transpose it and you apply another transposition, you end up with the same vector again. When you transpose an upper triangular, you end up having what? A lower triangular, and the vice versa. The one vice versa. So this is what I was asking you guys, that the transpose operation does not alter diagonal. It does not alter the diagonal. But as I said if it is a square matrix, although here you are seeing here to be 6, here to be 6, here to be 6, this you can say this maybe the diagonal. That is what you can see. Okay, so the diagonal is still, but if it's a square matrix, you see that it will come out perfectly, right? So when you transpose, the diagonal is not altered. Go and find out applications where when you do the transposition, okay, we are not supposed to, we can change the other part, but we don't want to change other parts. Go and find out in machine learning. Now, transposition is also compatible with matrix addition and scalar multiplication. So if you have this, what we can do is the transposition can have effect on them, then we add the same thing also with the scalar. So we can do this. These things are things that you are going to write scripts. During the lab, okay, you guys will have, or you implement it, right? Now let's look at this. This is also interesting. Look at it carefully. When two matrices multiply and we find a transpose, it's the same thing like we trying to reverse the order. And this is something that they even use in forgetting the algorithm they use, where if you look at it, it's like we are reversing, we are counting from the back, but we are transposing it. So when you look at something like this, where we have a vector, they are multiplying. That is deep learning, where you have vectors multiplying and you want to transpose it. It's far better if you reverse it, right? That means if you reverse the matrix, not a vector, when if you reverse the matrix and you transpose it and multiply in that order. So what he's trying to say is this is a matrix which they are multiplying 3 all the way to k, right? Now, I can also achieve the same result by using something like this, which I'll transpose this, which I'll transpose this, which I also transpose this, right? So look at this. Isn't it beautiful? So we are trying to multiply this. It's the same to me. It's the same thing as transposing. The same thing like transposing the matrices and multiplying the but in a reverse order. And this is what we use for our multiplication of matrices, okay, where it is only one dimension. I mean, if it is a row vector or a column vector, right? So here, if you look at this, we have a matrix. Let's take a matrix. Okay, so this is a matrix. This is also a matrix. Now, what is saying is that if you have this, okay, which we have this has been transposed, this also has been transposed, okay. If you apply a transposition, we can reverse, and we have this and that is what we did over there. So that's the reverse, and that is what we saw earlier on when we were trying to multiply to get that, where you have a matrix which is A, B, C, right? Then we also have another matrix which is what? E, F, J. Oh, sorry. This is my writing part. F, J. Okay. So if we keep it like this, we want to multiply, then it's saying that we have to what? Transpose the other one. So here we have this, then we have that. If I apply my transposition, this will reverse it back, and I have this. I'm missing it. Okay. Okay. All right, so let's continue. All right, so let's look at this. Now, which of these matrices is symmetric? Now, symmetric, as I said, if you transpose it, you still end up getting the same thing. I'm giving you guys just 1 minute. Get me the answer. Okay, so sorry, I muted myself. All right, so when you transpose this is what you get. Then let's transpose this one also to C. So the column becomes the row. So here one, you have what, three. Then here also becomes what, two. Then here becomes three. Then you have what, five. You have what, zero. You have what, two. You have what, zero. You have what, four. All right. So if you look at it, it's the same, right? So this is the symmetric, right? Note that all diagonal matrices, including the identity matrices, are symmetric. All right. Now let's talk about linear systems, which we will solve it. We'll do that. Okay. So linear systems of vectors. Now, if A is a matrix of dimension m by n, right? Then x2 is a column, vector, or you can also say it's 1 by n matrix. We can have something like this, which that is what we use for linear systems, right? So this is a practical scenario which we have done over here. Now we solving this. I remember engineering, they asked us to do this. We use the Gaussian elimination. There are a lot of algorithms out there that we use. Okay. All right. So this consists of linear algebraic equation. We have the n unknowns, and the x is what we actually were looking for, and the b, mostly in machine learning, we say that the b is the target. Okay, that's the b is the target. So you have your a over here, right, and you are looking for your target. Okay, so this one normally becomes your weight. That is your weight. Yes. So this is your target. So what we are getting over here is what we are going to train the computer to do, which you use Python, NumPy. That is what you are going to use, Python, NumPy. Or the NumPy library in Python. All right. But there's something that you have to understand, which we will use later on, which is the homogeneous linear systems. So when you have your b to be 0, that system is known as what? Homogeneous. Okay, and that is something that we're going to talk about it today, which is very, very important to us. Okay, so when your b is equal to 0, it's known as what? Homogeneous system or linear system. So let's look at this. I have a linear system over here, and I can get my matrix out. So this is 1, 2, 3, all the way to that. The same thing, I did that. Then so when you look at our unknown, these are our unknowns, okay, and this can be our target, right? So if we come out here, this is what you are going to get, something like this. Okay, so here we can use, what we learned, okay, where we can use the column by the row, or we can also use the row by the column, okay, any of them that you want. So this multiply this multiply that. Okay, this becomes 0, and that's what we have. And this one also attacks this, and this one also attacks this. But there's a better way to do this, which we are going to use. That is what they are doing over here. Okay, so this can also be expressed as this, which you see that this, which is the column that we spoke about, will be attacking each row. So the row multiply the column, the second row multiply the second column, the third row multiply the third column. And this is far more better, okay, for us to do than using the other one. If you look at it. Okay. Now, you remember we spoke about spaces and subspaces with vectors? We'll come back to this, but when you form something like this, okay, we are interested in these values. We are interested in these values a lot. These columns, we call them column space. We'll talk about it. Okay. Now, this column space can help us, one, to determine certain features. And these features are very, very crucial. So, if you have a vector, which of this, and remember, they can all be like a column. Okay, so when you have your matrix, those vectors can be a column in the matrix. Okay, those vectors can be in a column. All right, so we can have a matrix like this, where we have our vectors like a column, right? Now, we said the vectors are linearly dependent if and only if there's what? Non-zero solution. All right, so this, we have seen it already in vectors before, right? Where we spoke about the linear combination, right? And also the spanning. All right, the linear combination and also what? The spanning. Then the vectors can also be linearly independent. Okay, and we said the linearly independent, the only solution is when what? The x is 0. That means when this is 0, then everything collapses. Okay, but if you're able to get a value other than when x is equal to 0, that will let the thing get to 0. That means we say they are linearly or dependent. Okay, that means we are talking about homogeneous linear system. But if it is linearly dependent, that means the only solution is where x is what? Equal to what? 0. That means it's a 0 column vector. Now, when it happens like that, then we are back to the spanning. That means the vector B will lie in the span of the column vector. The vector B will lie in the span of the column vector. So let's look at this and let's do this together. So we have a vector, which is this. We can construct a matrix out of it, right? So this is the corresponding matrix we have over here, right? All right, so make your pen or get your pen, your paper ready. So this is our corresponding matrix. So this unknown, we don't know, but this is our target, right? So we have a linear system out here. Remember, it's not a homogeneous. If it's a homogeneous linear system, then we assume that the B is equal to 0. That means when the matrix multiply the vector, which is the unknown, it will be equated to 0. But that's not what we are doing. So we can form a system of linear equation where what we do is we multiply the x1, right? Can you do that by that? Then we also have what the x2, right? By 0, 1, then minus 2, then also do that for the x3. So x3 by negative 1, 2, 3, right? Now we have this. So if you come here, we expand it, we end up getting that x1 is equal to, x1 minus x3 is equal to this, then we be able to get this equation. Okay, can you confirm for me? Okay, some of you should just do that. Let's try to confirm one of them. So this, you get x1, then here becomes 0. Okay, so x1 minus x3 will be equal to b1. Yeah, b1, because here's 1, here's negative 1. So that means this is correct. Then we also have this, and we also have that. Look at this carefully, right? We can solve. Now, if you want to solve this, the first thing we can do is we make x1 a subject over here, right? Then here we can make x2 the subject. Then we come here, we come and do substitution. So once you do substitution, you end up getting this. Can you confirm for me? We make x1 the subject here, we make x2 the subject here, or we make s1 stand alone here, we make s2 stand alone here, then we come and do substitution over here, put it over here, we get this. Now this is our compatibility, which for the B over here. Okay, so it's supposed to be 1 minus 2, then 1. So 1, oh, where's my thing? Oh, so 1 minus 2, then 1 for the B, right? Now, if you look at it also, we are going to find out that some of the variables we refer to them, or the unknowns, we refer to them as free variables. Refer to them as free variables, okay? If you set all the B to 0, we are getting what? Homogeneous, right? That means everything over here is 0, and we are back to the homogeneous linear system. But if you don't want to do that, what can we do? We need to find a way to get the values. So by looking at it, you see that the x3 is a free variable. That means I can use the x3 to obtain the solution or the value for the x1 and also the x2, because this is the relationship between the x1 and the x2. This is also the relationship between what? The x2 and the x3. Right? Now, this is what happens when we call something known as a dependence. We learn in vectors where we spoke about the linear combination, that we have a vector. Okay, if you have a vector, can you express the vector using other vectors? Yes. Now, the other vectors that you have gotten, or the new vectors that you've gotten, do you have any of them that depend on other? If they depend on other, that means that is linear or dependence. If it doesn't, that is what linear independent. That's what we learn. If you look at it over here, you realize that, or you see that if I have, let's assume x is 1. Sorry, if x3 is 1. If x3 is 1, x1 become 1, then s2 becomes 2, then x1 2 becomes 2. Now this I can build any numbers, which is where we spoke about the spanning. Okay, so I can have a set of vectors out of this. Here, if I move to 2, I have what? 2, then what? 4, then what? 2. If I move to 3, I get what? 3, then I have what? 6, then I have what? 3, right? So you see, with this, look at the span. Have you seen the span? Now, this is making it linearly or dependent, because with this, I'm able to construct all these things, and that's not what we want. Okay, we saw this one way back when we're treating of vectors, right? Okay. All right. So not every linear system has a solution, okay? And that is something we'll find out next week, right? So we use other algorithms like what the Gaussian elimination, but that one, it has a lot of issues. You do it next lab. The next time that you guys have lab, we'll learn how to do this, okay? All right. All right, so let's talk about this, then we can conclude. I'll spend all the time here. All right, so we're going to talk about image kernel, rank, and what, and nullity, or nullity, or can we use the word nullity? We need to understand this so that when we are building our own algorithm, we are building our own systems, begin to make sense to us. So we have a matrix, and we say the matrix can all be what? We can have it in a column wise. That means we can have, if I say in a column wise, that means we can have column of vectors that can form a matrix. So we have a matrix, and they are formed by these column vectors, right? Now, we can have a subspace that span. Okay, if I say a subspace, you understand, that means another space that we can obtain from these columns, okay? And they are going to be what? Independent, right? They are going to be independent. Now, in matrices, when it happens like that, we call it an image. We call it an image, okay? That is an image, and that is the spanning or the span of that column vectors that can be used or that can be formed, okay, from the matrix. All right. This is also known as what? Column space. Let's take a practical scenario, then we will begin to understand it well. So let's have a matrix here, which is 1, then 2, then also have what 2 here, then have what 4 here, right? Now, if you look at this matrix, what can you tell me about this matrix? I also want to tell me what you see about this matrix. You can type in the chat. What do you see? Okay, so someone is saying 2by, all right. Okay, 2. How more answers? More answers. All right, so let's be quick. I don't want to waste time. So if you look at the column, if you look at the column, how many columns do I have? I have 2 columns, right? So anytime we're talking about the image or the column space, we are just talking about what? I mean, the columns, right? Joshua said the columns are dependent. Yes, the columns are dependent because if I multiply this by 2, I'll get it. So I multiply this by 2, right? So that means the image of this matrix is 1 because the only direction is the first one. The only unique direction is this. So that is the only unique direction. Apart from that, okay, this can be obtained by multiplying the first row by a factor or by a scalar. Okay, so that is Yomi. So when we talk about the image, we are just talking about that unique column, okay, that you can express in your matrix. So here, this can be expressed. If I multiply here by 2, I'll get 2. If I multiply here by this, so although this is having 2 columns, but the image is going to be what? 1. Okay, the image is going to be 1. All right. So when you get the image, the next thing is to find the rank. The rank too is another important thing. And the rank is also the dimension of your image. The dimension of your image. Now, your image talks about, the space. That's what they call the column space. Okay, the space. Now, I have 2 columns over here. All right. So if you look at this, if you pick this column, is 1, 2, right? So you will tell me that the dimension is what? Is 2. This one to the dimension is 2. But we got the image, and we go to know that the image is 1 because we can only use, the other entry is just a scalar multiplication of the first one. So the image is what? Is 1, right? Now, that means it is spanning a straight line. Okay, so here this dimension is a plane. Okay, so the image is just spanning a plane over here, which is let me take it again so I don't get confused. What I'm saying is that if you pick this column, it's spanning a plane, right? Which is r raised to the power 2. But because we can express one of them as the other, that means we can only pick this and the image will now be a straight line. It's going to be a straight line. It's not going to be a plane now. So once we know that the image is going to span a straight line, then when you find the dimension of this straight line, which is this, the dimension is going to be 1. And that is equal to the rank. So the rank of A is what? Is 1. And the rank can be 0 and can also be equal to the dimension of the column space or the column vector that we are dealing with. Now, when it is equal to the column vector, we call it what? Full rank. That is a full rank. We will talk about it. And the only time you have a zero rank is when you are dealing with what? A zero matrix. When you are dealing with a zero matrix. So we now seen the image, we've also seen the rank. The next thing we want to talk about is the kernel or the null space. The null space, the kernel or the null space. Now, this thing is also very, very important. You remember that we saw this linear equation formula where I said when b is equal to 0, that is what? A linear, homogeneous linear system, right? So when we talk about a kernel, what we mean is that what we are looking for is we are doing a transformation, which we are using the matrix to transform this vector to this, right? But our main interest is we want this vector, the b, to be 0. So it's like the matrix is like a machine. If I put the x inside, what I want out is 0. What I'm looking for should be 0. Okay, now this helps us to be able to remove all sort of dependencies in your data set and all these things. Because if they depend on each other, I mean, or if there's a, they call something, when I get a word, I will tell you. Okay, so it helps us to be able to remove that in such a way that if I use the matrix here to transform my x, okay, I'm supposed to get 0. And that one enables us to remove all sort of dependencies in our data set. Okay, so that is that. The second important subspace is the kernel, which we use it to annihilate, the vector. So the vector will change. So if the vector is a value, when we get a transformation, we end up getting what? 0 instead. All right. Now the kernel is the solution Z to the homogeneous linear system, as I said. So I did explain it over here that if you multiply, we are getting 0. So what value here that if you transform it by the matrix, you end up getting 0. And that is our kernel. Once you have your kernel, we can also find the nullity. The nullity is also the dimension of the kernel. The dimension of the kernel. And most of the time it's 1. Most of the time it is what? It is 1. But there's an important formula over here that when you add the rank to the nullity, you are supposed to get what? Your dimension, the column dimension, okay, which is this n. You're supposed to get this n of the matrix, which is the dimension, the column dimension of the matrix. So let's take a practical example here. So let's look at this. Let's consider this. Wow. We have this matrix. What is the image? What is the rank? What is the kernel? What is the nullity? Now, what can you say about this? Let's write down the column vectors where we have our column, which is 1, 0, right? I know it's 9 o'clock, guys. Hold on. This is C1. See, this part is very, very important. I need to, explain. 0, 1. Then also have C3, which is -1, -2, right? All right. Now let's look at this. If I want to get the image, you will tell me that this column is spanning what? This column is spanning this dimension, right? This one too is spanning the same dimension, right? This one too is spanning the same dimension, right? So let's look at it carefully and tell me, do you see that there's any dependency somewhere? Let's be quick, guys. Any dependency somewhere? Okay, where is it? Okay, the third column is dependent on the first two. Yes. So we can use the first two to build what? The third. That is some form of what dependency over there. Okay, so what can we do? This is where we have to look at it once again and say that, okay, so because we can form this using this, and how can you do that? So -1, -2, okay, can be written as -1, which is 1, 0, then plus -2, which is 0, 1. You can write it this way. Are you okay? Maybe when I'm finished with this, I'll stop here. Then next week we continue. Okay. Because it's not. I don't want to waste anybody's time here. Are you okay? All right. So if you look at it, you see that now these two, with these two, I can get this, right? So my image is going to span this Cartesian coordinate because I have three columns over here, which the dimension is what? Is 3, right? So if you look at it, you are going to see that these two, I can use it to get this. So this is going to be my image. So my image is going to span this coordinate or this Cartesian plane. Right. Then what is the rank? The rank is the dimension of the image. Now, if you are spanning the Cartesian coordinate, what's the dimension of the Cartesian coordinate? Is 2 what? Is 2 what? 2. So our rank is also what? Is also 2. Okay. Is 2. Then, if we look at the kernel, this is going to be a little bit, I don't have my writing pad, so it's going to be a little bit difficult. But if you take the slice, you can find out that your kernel will be x1 is equal to x3. Then x2, you can write the answer down, okay, so that you prove it is equal to 2x3. Okay. So your kernel is going to be 1, 2, then what? 1. And as I said, you can use it to construct. So once you have your kernel, then we can get our nullity. Okay. So the only way we can get the b to be 0, which I showed over here, okay, to be 0 is only one way. Okay. So our nullity 2 becomes 1. Now you saw the last formula that when you add the rank and the nullity, you need to get what? The dimension. So we saw the rank to be 2. So you saw the rank to be 2. So 2 plus 1 is equal to 3, which is equal to the dimension of our matrix, right? Okay. All right. So this is it. You can try it. All right. Okay. All right. So I will pause here, which we'll talk about it next week when we are talking about transformation. Okay. So any question? Any question? Any question?